Hello, in this lesson we are looking at graphing rational functions. Our essential question is, what are some of the characteristics of the graph of a rational function? What is a rational function? A rational function is a ratio or a fraction of polynomials where the denominator is not equal to 0. The inverse of a rational function f of x equals a over x is also a rational function. Graph of a simple rational function. The graph of the parent function f of x equals 1 over x is a hyperbola which consists of two symmetrical parts called branches. Here are the branches for f of x equals 1 over x. The domain and range for f of x equals 1 over x are all non-zero real numbers, meaning that you can have positive and negative values for x in our domain except 0, and positive and negative values for our range except 0. The reason why is our domain is based on what we cannot divide by, and right here, since I have x at the bottom of the fraction as part of my denominator, I cannot have it equal to 0 or else it will be undefined. Any function of the form g of x equals a over x where a is not equal to 0 has the same asymptotes, domain, and range as a function f of x equals 1 over x. Asymptote is a line that a curve approaches as it heads towards infinity. In our function f of x equals 1 over x, we have two asymptotes. We have a vertical asymptote where the denominator cannot equal 0, so in this case it's at 0. We also have a horizontal asymptote over here. This is where we have our vertical shift when we take a look at vertex form or the HK form of the function. Because I don't have anything added or subtracted to the function 1 over x, then my horizontal asymptote is at y equals 0. The end behavior of the function f of x equals 1 over x is as x goes to positive infinity, my function gets closer and closer to 0. And as x goes to negative infinity, my function gets again closer and closer to 0. Steps to graphing a rational function. First, find the horizontal and vertical asymptotes. Make a table of values using points to the left and right of the vertical asymptote. Include both positive and negative values of x. Plot the points. Draw the two branches of the hyperbola so that they pass through the plotted points and approach the asymptotes. Graphing a rational function of the form y equals a over x. Graph g of x equals 4 over x. Compare the graph with the graph of f over x equals 1 over x. Let's start by graphing the parent function 1 over x. First, what we need to do is identify our vertical asymptote and our horizontal asymptote. Our vertical asymptote is where my denominator cannot equal 0. In this case, it is at 0. So vertical asymptote is at x equals 0. I graphed the asymptote of x equals 0 over here using a dotted line. Our horizontal asymptote is given to us by the shift that occurs when we move our graph up or down on the y-axis. And we don't have a shift that moves over the y-axis, which is normally our k value. So our horizontal asymptote occurs when y equals 0. Here's the graph of the asymptote y equals 0, which is on our x-axis. Now, I've made a table of values and I've chosen values to the left and to the right of my vertical asymptote x equals 0. So the numbers I have chosen are -3, -2, -1, 1, 2, and 3. I'm going to use that to plug it into the function f of x equals 1 over x and simplify the expression 1 over x. 1 divided by -3 is -1/3. 1 divided by -2 is -1/2. 1 divided by -1 is -1. 1 divided by 1 is 1. 1 divided by 2 is +1/2. And 1 divided by 3 is +1/3. Now that I have my values for x and y, I am going to plot the points and Draw the two branches of the hyperbola so that they pass through the plotted points and approach the asymptotes. The graph of our function f of x equals 1 over x looks like this. Now let us graph the function g of x equals 4 over x. Start the same way, figure out our vertical asymptote and a horizontal asymptote. Our vertical asymptote is where we cannot have a 0 at the denominator, which in this case it's at x equals 0. Our horizontal asymptote is our shift in the graph in the y-axis, which we don't have a k value over here, so that is 0. Our vertical and horizontal asymptote for the function g of x equals 4 over x is the same as the vertical and horizontal asymptote for f of x equals 1 over x, which we already have on our graph. So now I'm going to choose points that are to the left and to the right of my vertical asymptote x equals 0 and plug it into the function and simplify. I chose to keep my values x equals -3, -2, -1, 1, 2, and 3. At x equals -3, we get 4 divided by -3, which is -4/3. At x equals -2, we get 4 divided by -2, which is -2. At x equals -1, we get 4 divided by -1, which is -4. At x equals 1, we get 4 divided by 1, which is 4. At x equals 2, we get 4 divided by 2, which is 2. And at x equals 3, we get 4/3. Plot the points and draw the two branches so that they approach the asymptotes. So now we're going to compare the graph of f of x equals 1 over x and the graph of g of x equals 4 over x. When we compare it, we get that the g of x is a vertical stretch of f of x by a factor of 4. So we've basically taken our parent function and stretched it by multiplying the function 1 over x by 4. G of x is further from the axis than f of x. Both graphs have the same asymptotes, domain, and range. Here are the steps for graphing a translation of a simple rational function. If you are given the rational function of the form y equals a over x minus h plus k, then you follow these steps. First, draw the asymptotes at x equals h and y equals k. Plot the points to the left and to the right of the vertical asymptote. Draw the two branches of the hyperbola so that they pass through the plotted points and approach the asymptote. We are graphing a translation of a rational function g of x equals -4 over x plus 2 minus 1, and then we are asked to state the domain and range of this function. Let's start by figuring out what our vertical and horizontal asymptote is. Our vertical asymptote is our h value, and it's given over here, which is the denominator of our rational function. To find our vertical asymptote, we want to find the value for x where x cannot equal 0. So what I do is I set x plus 2 equal to 0 and solve for x. X is equal to -2. This is the h value of the vertex form of our rational function. So I plotted the asymptote of x equals -2 right over here. Now let's find our horizontal asymptote. Our horizontal asymptote occurs right here. This -1 is basically saying that my entire graph is shifted down the y-axis by 1. So my horizontal asymptote occurs at y equals -1, which is my k value. So I plotted the horizontal asymptote of y equals -1. From here, I'm going to choose points to the left and to the right of my vertical asymptote x equals -2. To the left of the vertical asymptote, I've chosen the points -6, -4, and -3. To the right of the vertical asymptote, I've chosen -1, 0, and 2. I'm going to plug each one of these x values into my function and simplify the function to get my y value. I evaluated my function at each of the values I chose for x, and here are the values that I got for x and y. At x equals -6, I got 0. At x equals -4, I got 1. At x equals -3, I got 3. At x equals -1, I got -5. At x equals 0, I got -3. And at x equals 2, I got -2. I'm now going to plot these points and draw the branches of my hyperbola so that it gets close to the asymptotes. Here's our graph of the function. g of x equals negative 4 divided by x plus 2 minus 1. Our domain for this function is all real numbers except negative 2. The reason why it's not negative 2 is because I have an vertical asymptote at this point. And the range is all real numbers except negative 1, which is where I have my horizontal asymptote. Graphing other rational functions. If a function is not given to us in vertex form or HK form, then there are other ways that you can graph it to find the horizontal and vertical asymptote. So if we are given a function in the form y equals ax plus b divided by cx plus d, you can find the vertical asymptote at the line x equals negative d divided by c, because the function is undefined when the denominator cx plus d is 0. The horizontal asymptote is the line y equals a over c. Graph the function f of x equals 2x plus 1 over x minus 3. State the domain and range. Let's start by finding our vertical asymptote. Our vertical asymptote is where our denominator cannot equal 0, which in this case, we cannot have an x value of 3. To find a horizontal asymptote, we take our a value of our numerator and divide it by our c value of our denominator. Here my a value is 2, and my c value over here is 1. 2 divided by 1 is 2, which means my horizontal asymptote is at y equals 2. Here's our vertical asymptote of x equals 3 and horizontal asymptote of y equals 2. I'm now going to choose points to the left of the vertical asymptote, which I chose negative 2, 0, and 2, and to the right of the vertical asymptote, which I chose 4, 6, and 8. Going to use these x values, plug it into the function, simplify to get my y values. At x equals 8, we get y equals 17 over 5. At x equals 6, y is 13 over 3. At x equals 4, y is 9. At x equals 2, y is negative 5. At x equals 0, y is negative 1/3. And at x equals negative 2, y is 3/5. From here, plot the points on our graph and draw the two branches so that the hyperbola approaches the asymptotes. Here's the graph for our function f of x equals 2x plus 1 over x minus 3. Our domain for this function is all real numbers except 3, where 3 is our vertical asymptote, and our range is all real numbers except 2, where 2 is our horizontal asymptote. Another way of graphing the function of the form y equals ax plus b divided by cx plus d is to write it in vertex form or HK form. To do this, you could divide the function either by synthetic division based on what is in our denominator, or you could use long division to divide the function 2x plus 1 over x minus 3. I'm going to use long division to simplify this function. I have 2x plus 1 divided by x minus 3. Take 2x divided by x to get 2, because x divided by x is 1. So my quotient is positive 2. Since I am subtracting this part over here, I'm going to change 2 to a negative 2 and multiply it by x minus 3, which gives me 2x plus 1 minus 2x plus 6. 2x minus 2x add up to 0, and I'm left with 1 plus 6, which is positive 7. That is my remainder. So I can write the quotient of 2x plus 1 over x minus 3 as 2 plus 7 over x minus 3. Rewrite this in HK form by shifting the 7 over x minus 3 to the left and the positive 2 to the right to get 7 over x minus 3 plus 2. Here's my horizontal asymptote. That is at y equals 2. And my vertical asymptote is at x minus 3 equals 0, which means it is at x equals 3. I plotted the asymptote of x equals 3 and y equals 2. I chose some x values to the left of the vertical asymptote and to the right of the vertical asymptote, and I'm going to plug it into the function and then simplify. For x equals 8, we get y equals 17 over 5. At x equals 6, we get 13 over 3. At x equals 4, y is 9. At x equals 2, we get negative 5. At x equals 0, it's negative 1/3. And at x equals negative 2, y is 3/5. Plot the points and draw the two branches of the parabola so that they pass through the plotted points and approach the asymptote. And here's the graph of the rational function 2x plus 1 over x minus 3, rewritten in HK form or vertex form to be 7 over x minus 3 plus 2. Notice that our coordinate points and our asymptotes are the same as when we graphed it using the 2x plus 1 over x minus 3. The domain and range stay the same as well. Domain is all real numbers except 3, and range is all real numbers except 2. All right, that's it from me. I'll see you all soon.